is not quite complex. But ultrasound, because it is really another different kind of modality that uses totally different principles in image formation. So its physics is complex in a different manner, right? But not as and when I say complex, I'm not saying that it is difficult. It is easy to understand, but the physics associated with it is quite different and unique. Should I say unique from that what X-rays use for image formation. As you hear the word ultrasound, it is sound itself, just that there is this, should I say prefix? This one. There is that word ultra, but it is sound. When I speak, I produce sound which traverses through space or air to reach you as an individual. Just in case you are here with me physically, that's what happens. But sound is categorized. Sound is categorized into three. Sound is categorized into three. There is what we call infrasound. Infrasound, that is a sound with frequency lower than 20 Hz. I do not know whether you know what I mean when I say Hz or frequency. Frequency, first of all, is an English word. How frequently you do something, it means how many times you repeat the same thing in a given period of time. For example, if you eat 3 meals a day, sound is produced when an object vibrates. Sound is produced when an object vibrates. So, the number of times that object vibrates in a second, the number of times that object vibrates in a second will be the frequency in this case. So an object that vibrates less than 20 times or equal 20 times produces sound that has a frequency equal or less than 20 Hz. So those are just few times. So the sound that this object produces, that object which vibrates less than 20 times, the sound that it produces is what we call infrasound. There is that prefix infra. And what does infra mean? Infra means below. So if you don't call it infrasound, you call it below sound. And I'm not saying that you should write for me, you should write that for me in the exam that this is called below sound. No, I need that scientific one, which is infrasound. So why is it called below sound? It is because it is a sound which is below our hearing. We cannot hear that sound. It is way below the frequency that can be perceived by our ears. some animals have used it for communication. Animals like the leopards, animals like the elephants, they use infrasound for communication. However, most times, they produce sound that we can hear. Most times they produce sound that we can hear, but they can also use infrasound to communicate. For example, okay, not an example, like I'm just giving a scenario. Even if elephants have a distance apart of 200 meters and they stand in between them, they might be communicating, but you can't hear anything. They can be communicating without your consent. Maybe they can be plotting something against you without you knowing. But yes, they use that infrasound. The insects use it a lot. I think you have seen some insects coming close to each other, and then they start vibrating the antennas close to themselves. They are producing infrasound and they are communicating in that case. Now, with sound that has frequency between 20 and 20,000 hertz or 20 kilohertz, that sound with frequency between 20 and 20 kilohertz is the audible sound. That is a sound that we can hear with our ears. That is a frequency we can perceive. Anything that vibrates with frequency falling in that range produces sound that we can hear. When I talk, it's a vocal cord that's vibrating, so its frequency, because you're hearing me, its frequency falls within that range. But of course, as you grow older, that range keeps on diminishing. That's why all the people, they struggle a lot to hear things because the range has diminished. Was saying that as you age, this range or this audible range keeps on diminishing. Sound with a frequency beyond 20 kilohertz. Sound with a frequency beyond 20 kilohertz or beyond 20,000 hertz is what we call ultrasound. And the ultra, that prefix ultra, means beyond. Beyond sound. We can't hear that sound, so it is beyond the sound that we can hear. I think you have seen these people naming their businesses like Ultra Farmers, Ultra Supermarkets, Ultra whatever. It means beyond what you can imagine. Ultra Farmers, beyond farmers. It shows that the farmers is you can go there and get whatever that you need and authentic things. I don't know whether they are truthful to that name, but that's what it means. So, since it is a sound that we can't hear, you can get surprised that some animals are using it for communication. One of those animals is a bat. Bats use ultrasound for communication, to look for prey, to look for mates. Bats don't see at all, even at night. Of course, we have all grown thinking that bats see at night, but they don't. The reason why they move at night, okay, they can see, but they have a very poor eyesight, even at night. The reason why they move at night, it's because at night there is less interference. Like there's less noise coming from different corners, so there is less interference between its ultrasound and the noise coming from different corners. So the environment is calm, so it can clearly send this sound and get echoes efficiently and effectively, and so it can move and do not even knock obstacles. Other animals which use ultrasound include the whales, the orcas, the dolphins. They all use ultrasound for communication and other things. And surprisingly, the way the ultrasound machine works, sending these ultrasound beams into the body, getting back the echoes, reconstruct images, they say is the same way these animals use this ultrasound for. They also send ultrasound beams. These beams get reflected from different obstacles. They come back to the same animal. Then the brains of these animals interpret the echoes that come back, reconstruct what is actually these obstacles that have reflected these echoes, and get to know what is where. Just like how a fish, this normal fish, can feel the vibration of water when something is moving on it without even seeing it, without even seeing whether a boat or a ship. Even if a fish is maybe a few kilometers away from the ship, it is not seeing the ship, but because it is creating some vibration in water, the fish can feel it. So, by the way, dogs can hear part of ultrasound. They can hear from 20 Hz to about 40 kilohertz. They can hear beyond us. That's why if you are maybe moving in the jungle with a dog, a very calm environment, sometimes you see it putting its ears up, listening to something or hearing something that you can't even hear. And that's what makes some people think that dogs can hear ghosts, can hear what? That's not the truth. Just like how they say cats can see ghosts, can see what? It's just that they have a very good eyesight than us that can even glow in the night. It's not that they see ghosts. Okay. So sound cannot travel through vacuums. Sound cannot travel through a vacuum. Sound needs a medium to travel. Sound needs a medium to travel. It doesn't travel through a vacuum. So it can travel through air because air is matter. So it's a medium. It can travel through metals, wood, and other things. As long as it is a medium, sound can travel through it. In medical diagnostics, ultrasound is produced by what we call the piezoelectric crystals. An example of a piezoelectric crystal is a quartz crystal. I know all of you have seen this word quartz because you have all put on watches before where we have the word quartz. Quartz is not a manufacturer of watches, as most people think. Quartz is a crystal in your watch. That crystal, it converts the chemical energy from the battery cell of your watch into mechanical energy that moves the hands of your watch. Without that crystal, even if you change a battery, the watch will never work. So if that crystal fails, that watch is dead. Now, anything that converts energy from one form to another is called a transducer. Anything that converts energy from one form to another is a transducer. Transducer, I think, is not a new word to you. There we have so many examples of transducers. An example is a microphone. When you speak on a microphone, you give this microphone mechanical energy, which is sound. Sound is a mechanical energy. And then this microphone will convert that mechanical energy into electrical energy. So that is a transducer. A loudspeaker is a transducer because it converts electrical energy into mechanical energy, which is sound that we can hear. Yourself, you are a transducer because when you don't eat food, a lot of things in your body can shut down. Why? They need energy to work. When you take food, you're taking in chemical energy, which can be converted into other forms of energies within your body, depending on the tissue's need. I'll talk about the heat generated by your body. It's as a result of metabolism that is taking place in your body. That is as a result of digestion. In that process, chemical energy is being converted into heat energy that warms up your body. So you are a transducer. So the piezoelectric elements that we use for production of ultrasound are transducers. The unique thing about them is that they are two-way transducers. They can convert electrical energy into mechanical energy, which is ultrasound. When this ultrasound goes into the body, the structures reflect this ultrasound. The echoes come back to the transducer. The echoes are still mechanical energy. They come back to the same transducers. And then these transducers convert these echoes, these mechanical waves, back into electrical energy. Then those echo voltages are taken into other systems of the machine, analyzed, and then the image is formulated on the display. The quartz crystal that we use in the watches is a naturally occurring piezoelectric element. It has found its utilization in watches. In probes or in ultrasound, quartz crystals are not efficient at producing ultrasound. The piezoelectric crystals that we use for production of ultrasound are artificially made, and they are made up of lead titaniate, zirconate. Okay. Sound is a wave, and it's a mechanical wave. And sound has speed. It moves at a speed, and this speed depends on the medium through which this sound is traveling. An example here, they are showing you that speed of sound in the air is 330 meters per second. In soft tissues in the body, the average speed is 1540 meters per second. This speed is much slower. This sound is much slower than the speed of electromagnetic waves. Speed of electromagnetic waves like light, X-rays, gamma rays is about 300 million meters per second. That is 3 exponent 8 meters per second. So sound really travel very slow. That's why lightning and thunder occur at the same time. But here, when you're just on the ground here, what do you see first? You see light first, and then thunder comes in after seconds, some few seconds. But both of them occur at the same time. For example, if we're in the clouds, you would see that lightning and sound, they occur at the same time. But when you're on the ground, you see light first, then a few seconds pass, and then you hear sound. So, the speed of sound depends on how stiff a material is, not how dense a material is. I know from our secondary schools, we have all been taught that the speed of sound depends on density. It's not 100% true that it depends on density, because there are some materials which are so dense, but the speed of sound is so low in them. An example, lead. Lead is so dense that we even use it for radiation protection. But the speed of sound is slow in it. So that disqualifies the statement that speed of sound depends on density. The true statement is speed of sound depends on the stiffness. Stiffness is the compressibility of a material. All right, members, is everything okay? Do you have any questions so far? I
think we are good.
Okay. I was still saying that speed of sound basically depends on the stiffness of a material, and stiffness, I said, is a compressibility of an object. The more compressible an object is, the lower the speed of sound in it. Air is so compressible, so the speed of sound is slow in air. In the body, it is the bones that are stiffer. So the speed of sound in the bones in the body is higher than the speed of sound in other structures. But surprisingly, we don't use ultrasound to image bones because this sound will not go through bones. for reasons that we are going to see, because that's all physics. So sound as a wave. Sound has acoustic, what we call acoustic wave variables. There are certain things that vary as sound is propagating through the medium. Pressure varies, density varies, temperature varies, particle motion varies. But before we understand this acoustic variable, let me first make you understand how sound travels from one point to another. Some of us that have gone through UPE schools, we used to make these lines at the powerhouse or at the kitchen when we are going to get food. And the way we used to make lines is that we used to be skin to skin. Like you can be skin to skin because you don't want any fluke to come in between you or yourselves. Because everyone is striving to reach and get food. So you don't want anyone to come anywhere in front of you. So you make a line that you even your temperature even rises because you're getting the temperature from the person in front of you and from the one at the back of you. You smear yourself with sweat of other people. So when someone comes at the back of the line and pushes that person at the back towards the in front, like to push, to push. You push that person towards the front, the entire line can fall on ground. What I'm trying to say is, it is the last person who has been pushed, but why is it that the entire line will fall? It implies that that energy was transferred from the last person and felt by everyone almost. So, for example, if this is a particle here, and you have another one here, and another, and another. When you push this one will come and push this one will come and push that, and that will come and push this. But when this one pushes this, it doesn't continue. It will come back to its position. As it is coming back to its position, this one goes to push the third one. After pushing, it will come back. Then the third one, which was pushed, will go and push on the fourth. After pushing the fourth, it will come back to its main position. So when this one is interacting with this one, they are changing, or they are exchanging energy. This one is transferring energy to this one. And then when this one moves to hit this one, it transfers energy which was given to this one. And then this one transfers energy to that. That's how energy can be transferred from one particle or one molecule to another. So that's why they always say that sound wave moves, but the medium through which it is moving does not move. Because of this, the particle just gets displaced and then comes back to its mean position. It is displaced to go and transfer energy, then afterwards it will come back to its mean position and wait for another push. So you realize that matter does not move from one point to another, but energy can move from point A to point B without this matter moving. And this is what will be happening. So going back to pressure, density, temperature, particle motion. When this particle here comes and pushes this, particle 1 and 2 will come so close to each other. As this one is coming to, as 1 is coming to 2, they come close to each other to exchange energy. And as they are coming close to each other, they compress themselves, meaning that the pressure between them increases. And also the density increases. Density is the number of I should say particles or per unit volume, something like that. So when the particles come together, the pressure increases in between them, and also the density. As when one goes back to its mean position, there is a gap created in between them. The pressure decreases, and also the density decreases in the same way. So pressure and density will keep on varying because of that. Temperature, you know, when these particles come and knock each other, they're actually rubbing over each other, just like getting two hard surfaces and you rub them together. You rub both of them against each other. There is heat that develops in between them. Or when a tire, for example, a car has been moving and then maybe there's a certain hump and one tire tries to drag so much so that the car can move, but the car is not moving, drags itself against the ground. It develops heat because of that friction. That kind of rubbing develops heat. So even as these particles keep on hitting each other, they are actually rubbing over each other, developing heat. Particle motion. The displacement, when the first particle has been displaced, because it is still having a lot of energy, it's going to be displaced a greater distance and then comes back, because the wave is still having a lot of energy. But as the wave propagates through molecules, it will keep on reducing its energy. The energy will keep on being attenuated. By the time it reaches this particle X, the energy has reduced, and so this particle X is not going to be displaced as much as the first particle was displaced. So you realize that the particle motion also varies. The amplitude is higher at the beginning, but the amplitude becomes lower and lower until the last particle. So in daily life, sound travels from the speaker and is heard by the listener. It is something which moves or which travels. So particles will keep on oscillating back and forth as sound waves are traversing through them. At any point in the medium, the variables increase and decrease in repetitive cycles as the wave travels. So we have what we call longitudinal and transverse waves. Longitudinal waves, these are the waves whereby molecule will keep on being displaced in this direction. For example, if sound comes from this side, the sound is coming from this side. This molecule will keep on moving to and fro like this as it is transferring energy. And also sound will keep on moving in the same direction. This is called a longitudinal wave. the particle motion is parallel to the direction of the wave's travel. We call that a longitudinal wave. Whereas a transverse wave, this is the wave whereby the particles which are actually creating this wave or transferring this wave are vibrating perpendicular to the wave's travel. For example, water waves. Water waves. The particles just move up and down while the wave is moving horizontally. If you want to experiment it, those who have a swimming pool at home, try to drop a stone in the middle of the swimming pool to create those waves on the surface of water, and then drop a piece of paper on that surface of water. You realize that the piece of paper is just moving up and down, but doesn't move with the wave. The piece of paper is just moving up and down. That demonstrates what the molecules are doing. They are just going up and down, and then the wave is moving horizontally. That's a transverse wave. However, whether transverse or longitudinal, they are all presented by a sinusoidal kind of wave. They are all represented by this sinusoidal nature of illustration. For sound waves, these crests they represent points when molecules come close to each other and exchange energy. The troughs, they represent when molecules are moving far apart after exchanging energy. So the molecule will come, exchange energy, and then goes back. It will come again to exchange energy, and then goes back. That can be represented by this sinusoidal illustration also. The distance from one crest to another crest is a wavelength, or a wavelength is the length of one cycle. This is the basic physics that you looked at in your A-level and even the bridging courses. Okay. Compression and rarefaction, but compression versus rarefaction. The points where molecules come close to each other to exchange energy are called compression regions, whereas the points where molecules move far apart are called rarefaction regions. For example, when the molecules are coming close to each other like this, here they are exchanging energy, here they are moving far apart, exchanging energy apart, exchanging energy apart. As one molecule is coming, going back, coming, going back. So this compression region is a crest, whereas the rarefaction region is a trough. So if I draw my wave as this, and I say this is a sound wave, I'll be meaning that these crests are compression regions where molecules come close to each other to exchange energy. And these are rarefaction regions where molecules move far apart after exchanging energy. This is a video, but of course it won't play on this platform. There is this presentation in the PPT. There is a PDF, I think, and also a PPT. If you download the PPT, you'll be able to play the video. It is just illustrating everything that I've talked about from the beginning. So sound wave description. In sound waves, we have some terminologies. In sound, we have some terminologies like frequency. I've already defined what frequency is. That is the number of wave cycles produced in 1 second. Period, that is the time it takes to complete 1 cycle of a wave. Wavelength, that is the length of a cycle of a wave. Propagation speed, that is of course the speed of sound in a medium. Amplitude measures how energetic the beam is. And intensity, that is the quantity of the beam passing through a unit area. So these are terminologies which you come at even in the A level and your bridging courses. I'm sure you're still remembering these things. Frequency, period, wavelength, propagation speed, amplitude, and intensity. As I was starting, I told you that the speed of sound depends on the medium and specifically the stiffness of the medium. Wavelength of wave is dependent on the source and the medium, but primarily depends on the source. Depends on the source primarily. Frequency, period, amplitude, intensity depend all on source of sound, because the frequency is the number of cycles produced in 1 second, and it shows that, it implies or it means the number of times, means the number of times an object vibrates to produce sound. Period, how long this object vibrates one time. That will be the period. How long this object vibrates one time. That is the period. So it's the time it takes to create one cycle. Amplitude implies the energy of the beam. How long does an acoustic variable get away from its equilibrium? That is the amplitude. So let me say, if I draw my wave like this, I always put an equilibrium position, always zero position. How wave pressure, how much pressure increases from 0 to the maximum will be the amplitude, or how density increases from 0 to the maximum, that will be the amplitude, and it measures the energy of the beam. Intensity, the amount of energy of this beam that is going through a unit area of a medium. That will be the intensity. So this frequency was studied by a German physicist called Heinrich Haas, and that's why the units of frequency were in honor of his work. So they named it Haas. Period and frequency, they have a relationship. When frequency increases, the period reduces, because frequency is equal to 1 over period. So you see that frequency is inversely proportional to period. A constant is always 1. If you did mathematics, frequency is inversely proportional to period. That implies that when the frequency increases, the period reduces. And in actual sense, it is true. Like when you look at it, when you think about it, frequency means the number of cycles in 1 second. If you want to pack more cycles in that same second, that means you must reduce the time by which each cycle is produced, such that you can have more cycles in 1 second. I repeat, when you look at it like using your common sense, it is true. Frequency implies the number of cycles of a wave produced in 1 second. The number of cycles of a wave produced in 1 second. So if you want to increase the number of cycles in that second, you must reduce the time it takes to create a cycle. When you reduce the time it takes to create a cycle, that second will be able to accommodate more cycles. Does that make sense, ladies and gentlemen?
Yes.
Yes, sir. Okay. This is a repetition of what I talked about at the beginning. So, frequency. The reason why we talk about frequency so much is because it is very important in diagnostic ultrasound because of its impact on resolution and penetration. Because it has an impact on resolution and penetration of the beam, frequency is controlled by the choice of a transducer. We have transducers that have higher frequencies. We have transducers that produce low frequencies. By the way, what I didn't tell you is that the frequency we use for diagnostic purposes ranges between 1 megahertz to 20 megahertz. Much as I said that sound with frequency beyond 20 kilohertz is ultrasound, not every frequency range, not every frequency above 20 kilohertz that can be used for diagnostic purposes. No. The frequency we use for diagnostic purposes has a range that is 1 to 20 megahertz. So, frequency is very special in ultrasonography because it has an impact on resolution and penetration. The higher the frequency of ultrasound beam, the lesser the penetration, but the better the resolution of the image. So higher frequency beams produce better images, but the beam does not penetrate deeper. Whereas low frequencies, they penetrate deeper, but they produce poor resolution images. Some people confuse frequency with energy. When you talk about high frequency, for them, they think that high frequency penetrates deeper because it is high. Frequency is different from energy. When the energy of the beam is high, yes, it can go far. But I'm talking about frequency, which is just vibration, number of times the beam vibrates or the molecules vibrates per second. The higher the frequency, the less, the better the image resolution, the poorer the penetration. The lower the frequency, the poorer the resolution of the image, the better the penetration, the deeper the penetration. Now, why is it that high frequency does not penetrate? That's where the question is. Why is it that high frequency does not penetrate? The reason is, when you want to develop heat in your palms, when it is a cold temperature, it has rained, it is too cold, your fingers are getting very cold and stiff. What you do is to rub your palms to develop heat. When you rub them slowly, do you generate heat in the palms? No. But when you rub them very fast, they generate heat. So when the frequency is high, higher frequency, it is equivalent to rubbing your palms very fast. So at high frequencies, instead of these molecules transferring energy deeper, they are actually converting it into heat. So the energy becomes absorbed so fast because it is being converted into heat. Whereas at low frequency, it is equivalent to rubbing your palms slowly. The conversion of energy into heat is not as high as at high frequency. So the beam does not get absorbed so fast as that in high frequency, so it can get deeper. So you cannot use a high frequency when you are scanning an obese patient. Patient is so huge, a lot of fat, that means the beam has to go through fat first before it even reaches the organs that you need to look at. So you can't use a high frequency on a fat patient. You use low frequency because that has the ability to penetrate and reach those organs. But if it's a small person like me, even my abdominal organs can be seen by high frequency. I don't know, but that's what I'm assuming. So that's the importance of frequency in ultrasonography. All right, so this one talks about period I will talk about more of the period when I'm talking about the pulse ecosystems. Let me first reserve it for the pulse ecosystem because it is very important there, and there's what we use it for. So don't get scared. This subject is not for calculation, but in your free time you can do the calculation. You can, those who have done math, and get the answer here. But I'm not going to talk about mathematics. So as frequency increases, the period reduces. I've already told you that frequency is inversely proportional to period. Frequency is inversely proportional to period. The speed of sound, I already talked about it, and I say that the speed of sound depends on the stiffness, not density. And I say that stiffness is a compressibility. How? Because stiffness is related to compressibility. The more the object is compressible, the less stiff it is, and so the speed of sound will be low in that material. Sponge is highly compressible because of low stiffness. So stiff material such as a rock has low compressibility. Still talking about what I already talked about. Stiff materials in the body could be like bones, gallstones, hard plaque. This is where speed of sound is higher in the body. All these things I've talked about them. Here they are just showing you different speeds, different materials and corresponding sound speeds in them. Air, the speed of sound is 330 meters per second. The lung is 600. Skull bone is 4,000. You realize the skull bone represents all bones, so you realize that the speed of sound is higher in bones. In fat is 1460. Water 1480. Liver 1555. Muscles 1600. Now, why did I group them here? These are basically called soft tissues. We use sound to image soft tissues, and the average speed of sound in soft tissues is 1540. If you look at all soft tissues, have all their speeds, the average speed in all soft tissues will be 1540. So from now on you're going to see that we shall be only talking about 1540 meters per second or 1.54 millimeters per microsecond. That is the speed of sound in soft tissues. But of course, we know that the speed of sound is different in different tissues. These ones are the outliers. The speed of sound in the bone is very high. In the lung is 600 because the lung is a mixture of tissue and air. In air, it is 330 meters per second. And we shall see the effects of these speeds when it comes to knowing how the image is actually created. Wavelength, that is the length of one cycle. I really don't want to go much into that because I'm sure you understood. There is the formula for the speed of sound is C. C is equal to lambda f, whereby f is the frequency, lambda is the wavelength, the C represents speed of sound. If I want to calculate wavelength, I will make wavelength the subject. It will be wavelength is equal to the speed of sound divided by frequency. You just feed in your values and then calculate the wavelength. When frequency increases, the wavelength reduces because of an inverse relationship. You see, wavelength is inversely proportional to frequency. When one increases, another reduces. That's what it implies. And a summary of how a wave is and different things on it. A cycle, I told you that one cycle It can, okay, you can say from here, from one crest to another is one cycle, or from here to here. So a cycle should have one crest and one trough. A cycle should have one crest and one trough. So this is one complete cycle. The distance of a cycle, the length of a cycle is a wavelength. You can also measure wavelength when you look at the distance between two crests, two adjacent crests. That will be also a wavelength. And I told you that the amplitude is how much a wave variable gets away from its equilibrium. Like for example, how pressure varies from 0 to maximum. Pressure varying from 0 to maximum, that is the amplitude. Or density varying from 0 to maximum, that will be the amplitude. Yes, and this marks the end of this presentation. I hope most of the things which I have presented have been well understood. Right. Someone unmuted and clapped. Okay, thank you. So let me welcome questions. Some highlights on how low frequency brings. I've told you that a higher frequency, molecules are vibrating so fast, they are rubbing each other. Instead of transferring energy, they are converting it into heat. So higher frequency, the energy does not go far. The beam doesn't penetrate far. The vice versa is true. Low frequency, the molecules are not converting energy into heat that much, so the beam can go far. When I talk about one, that means that the vice versa is true. How resolution is brought about, we shall understand that. We are still going on with this course unit. There's a time for resolution. We shall look at it. A reference book is Sonography Principles and Instruments. Sonography Principles and Instruments.